Gotta find it. All right, so we had the first round. Seemed like everything went smoothly, I think. I didn't see anything that was totally unexpected. So here are the first round results. Some teams changed names, so I'm not exactly sure who's who of some of the new names in here. Glad to see that 30 Rack is making money. Always good to see. Rack and Roll actually lost money. Might be able to figure out why that was. So here's a plot of sales versus price. So it looks like people were setting the kind of the average price was around the $60 range. Just for, I can make this bigger. Just for the sake of interest, I plotted the sales versus price for this round against the sales versus price for the first round of the practice game we did earlier. So the orange is the current real game and the blue is the first round of the practice game. So we see prices were set a little higher and demand was a little lower. Here is the sales versus price by teams. So there was one team that set some fairly low prices, got some fairly high demand, and there was some other things going on too. Just kind of scanning through the results. If you look at construction projects, everybody is building something. And you can tell by the amounts, you can generally make a guess as to what they're building. Probably this could be, for example, a plant and 5 production lines. This is clearly a warehouse, etc. We look at finished goods inventory, we see that all but 3 teams have 0 finished goods. So that means that all but 3 teams probably have back orders. And we see that 2 teams have a lot of this is dollars, not units, keep that in mind. But a couple of teams have a lot of finished goods, including Rack and Roll. You may recall Rack and Roll is in last place, but they didn't sell much of anything, so they have built up some inventory that may lead to future profits. Everybody's got some amount of raw material except for party CDs. Oops. What else do we have here? So earnings per share, 2 teams, well, one was negative, Rack and Roll, but they've got lots of finished goods. And 1 team was essentially 0, whereas 3 teams had a very good earnings per share ratio. We had a couple of teams declaring dividends, notably CD's Racks is declaring a $1 dividend. Oops, I got it, sorry about that. And look, Rack at Us is declaring a 10-cent dividend. And there is 1 pending insider trade. CD's Racks plans to purchase 1,000 shares of their own stock. And that will occur next period. So here are the sales figures. 2 teams, CD's Racks and Rack and Roll. Rack and Roll actually had 0 sales. I'm sure if we looked at their prices, they were very high. And CD's Racks did not sell very many. On the contrary, there are some teams, so I believe in the first period, your maximum production rate is 4,000 units, so we see many teams that will have back orders. Now, does anybody have any questions or comments or issues about the first round of the game? Every team's results looked like what you expected them to be. In particular, the team that sold 0, that was planned, I'm guessing, right? Actually, I could go back and, let's go back and look again. Actually, I can't. I'd have to go back and look at their prices, but I'm guessing that they were setting prices down here like 100, and that's what happened. So any questions? Just unmute yourself. We're all good? All right. Okay. So today's topic is inventory. Slides are posted. All right, so today's topic, as I said, is inventory. If you know anything about business or industrial engineering topics like that, you probably heard of things like just-in-time manufacturing and lean manufacturing. These are sort of kind of policies or managerial programs. And under these things, the idea of having inventory is kind of known to be a bad thing. But generally speaking, I hope to convince you that that's not always the case. So we want to answer questions like, why do firms maintain inventories? What's the alternative to maintaining inventories? What are the positives? What are the negatives, etc. Now, it's also important to distinguish between different types of inventories. So in the game, we have two kinds of inventory. We're worried about raw materials inventory and finished goods inventory, but in the real world, we also have something called in-process inventory, or often called WIP, for work in process. And so like raw material inventory is where this whole just-in-time philosophy is talked about. So what just-in-time manufacturing means is that the vendors that are supplying things like raw materials to some factory, they schedule the delivery of their raw materials so that they arrive just in time when they're needed by the factory. Right? So for a while, this was kind of heralded as a big deal in logistics and things like that. But on closer examination, basically what it's doing is the manufacturer is passing off the inventory carrying costs onto the supplier. But typically what happened is the supplier would have to rent warehouse space just down the street from the plant and then deliver it when it was called for. You hear a lot more these days about lean manufacturing, and the lean manufacturing is this whole thing, but one of the edicts of lean manufacturing is you should have very, very low work in process inventory. So they seek to get that down to a minimum. And then finished goods inventory, whether you have finished goods inventory or not, is basically almost like asking, do you make to stock or do you make to order? So make to order means you don't even start making something until you have an order for it. Whereas make to stock means you keep an inventory of finished goods such that when you get an order, you can immediately ship to the person that ordered it. Okay, so there are some positives for having inventory. In the case of finished goods, if you make to stock, then you can deliver to your customers immediately. So the customer avoids manufacturing lead time and they are happier. Another common use of finished goods inventory is it allows you to smooth variable demand. Right? If you were filling your demands kind of on a daily basis, then you would be very, very busy during busy periods and very, very unbusy during unbusy periods. And you can smooth this out by keeping inventory. So a good example I've actually witnessed myself is peeps. So I don't know if everyone knows what a peep is, but it's this yellow marshmallow bird thing that they sell typically around Easter. I think everybody must know what a peep is. And you may or may not know that these peeps are made right across the river from Lehigh at the Just Born Company. And in fact, that factory manufactures all of the peeps for the whole world. It's also true that peeps are sold almost exclusively within a few weeks of Easter, because they're kind of an Easter candy, if you will. But in fact, they make peeps at the Just Born factory 24 hours a day, 7 days a week for the entire year. So what they actually do is by doing so, they can use one production line and make all the peeps they need for Easter, but it takes them all year to do it, right? If you had to make all of the peeps for Easter in the month coming up to Easter, you'd need 12 times as many production lines, right? You see what I mean by being able to smooth out variable demand by having inventories. And that's often a very useful thing to do. So the negatives, so obviously the main negative is holding costs. It costs you money to store stuff, particularly in the case of finished goods. So you need space to store the stuff. You need people to handle it. And often more expensive is there are interest costs. So in other words, Just Born spends this money ahead of time to make all of these peeps. The peeps just sit there in inventory. So whatever interest rate you're paying on that money it costs you to build them is another holding cost. So when you think of holding costs, you got to think of buildings, people, and interest. And just because you have some finished goods inventory doesn't mean you still may not have back orders, right? Now, that will only happen if you don't have enough inventory, but you still could have back orders. Back orders are generally considered bad, customer goodwill, etc. So that's sort of an introduction to inventory in general. We're going to talk about two very specific, very well known, and pretty simple inventory problems. In fact, the second one we've already seen. We're going to look at it more closely this time. The first is called EOQ, or Economic Order Quantity Model. And what it helps us to do is understand the trade-off between many small orders and a few large orders. So the way I think about it is we're manufacturing some product and we're putting it in inventory, so we're making the stock, but we make production runs every so often. So it could be every 2 months we'll set up the factory to make this product, make the product and put it into inventory, and then 2 months later we'll do the same thing over again. All right, so this model has a lot of assumptions, many of which are probably not realistic, but later we can talk about how you can relax those assumptions. The first assumption is that demand rate, which is equivalent to the depletion of inventory, is known and constant. So the units are disappearing out of your inventory at a constant rate. Obviously, we know that's not true. We know that demand is random. Shortages are not permitted. We don't allow back orders, and there's no lead time on orders. So what this means is if you decide you need to replenish your inventory, build your inventory back up, just have to snap your finger and it will jump back up. Obviously, that is not realistic either. There's always some kind of lead time between the time you decide to replenish inventory and the time it's replenished. Okay? In terms of costs, we're going to assume that each order has both a fixed and a variable cost. Okay, so the specific model. So that's why I say the way I envision this is we have, let's say once every couple of months we make this stuff. And so the first thing we have to do is we have to set up our production line to make it. And the setup of that production line is a fixed cost. Every time we decide to make a production run, there's a fixed cost of K dollars. And then plus there's a variable cost, C dollars per unit. So that's the production part of the cost. Then there's the holding costs that could involve, that just, you know, that involve the cost of holding stuff in inventory. There's only one decision variable in this model, and it's Q, the number of units to order each time an order is placed. The best way to understand this, sorry. So every T time units, we're going to order Q units, or every T time units, we're going to make Q units. The demand rate is constant, and we're going to call that lambda. So that would be lambda is the number of produced units consumed per time unit. And then I of T is the inventory level at time T. You have the annual interest rate. Okay, so I wanted to get to this graph. So this is what's called the inventory sawtooth curve. So we're plotting the inventory level versus time. So we start off with Q units in inventory, and then that inventory is depleted over time. Demand rate is constant, right? And then at some point we replenish the inventory. So we make more units, put them in the inventory, and the inventory jumps back up. So the height at which this, and then it just keeps going. So this is called the inventory sawtooth curve. The height that it jumps up is Q units, and the time between orders is T time units. So inventory on the y-axis, time on the x-axis. Now, because we can replenish instantaneously, as soon as inventory hits 0, we just go get our Q more units. Real world, that's not realistic. It actually takes time to do that. But in this simple model, we don't have to worry about that. All right, so we're trying to decide what Q should be. So here's what the sawtooth curve looks like for two different values of Q, right? So which value of Q is better, the blue one or the red one? Okay, so what you can see is that the average inventory is higher for the red curve. How would we figure out what the average inventory is for that red curve? Well, it would simply be the area under the curve divided by T. Because of the simple geometry of the case, you can also see that it would be exactly half of this value Q. So the average inventory for the red curve would be in the middle of the red curve, and the average inventory for the blue curve would be in the middle of the blue curve. And so when we have the smaller value of Q, we're carrying less inventory on average, and thus our inventory costs, our holding costs are less. On the other hand, when Q is small, we're ordering more frequently. And remember that every time we order, there's a fixed cost. We're calling it a setup cost, right? So there's a trade-off between the setup cost and the inventory holding cost. We're trying to find the value of Q that trades those off and produces the minimum cost. All right, so now we're going to do some math. It's actually high school level math. Not hard at all. So the ordering cost, it has a fixed component K plus the variable component C dollars per unit. We have a holding cost. We're going to just assume that the holding cost is I times C. So that's, you know, for every unit, we're going to pay interest on the variable cost. We could easily add in, if we wanted to, costs for buildings and people. That's easy enough to do. But to keep things simple, we'll just have the holding cost be I times C per unit. And then the average inventory on hand will always be Q over 2, as we argued just a minute ago. And again, the trade-off is between inventory carrying costs and order fixed cost. Okay, so lambda represents the rate at which inventory is depleted, or equivalently represents the demand rate. It would be in units per time unit. And so you can see here that in T time units, we deplete Q units of inventory, thus lambda can be represented as Q over T units per time unit, or stated differently, we can rewrite T as Q over lambda. So we'll use that in a minute. So order cost, every time we order, it's this K plus CQ. Our inventory holding cost is the per unit holding cost times average number of units times T, the length of the cycle. So this is the cost per cycle, just to be clear. Like, 1 tooth of the sawtooth curve represents a cycle. All right, so each cycle we have to pay H per unit times this many units times the length of the cycle. We can substitute in for T, this Q over lambda, like we saw in the last page, and simplify this down. So when we add the two costs together, we get this equation. All right, so this is the cost per cycle. And it's a quadratic equation, which we could easily solve for Q. But is this what we should be minimizing? This is the cost per cycle. And the answer is no, this is not what we should be minimizing, because the lengths of the cycles are different depending on the value of Q, right? For the red value of Q, the cycles are longer than they are for the blue. So what we really want to do is minimize the cost per time unit. If we minimize the cost per cycle, the answer would be to have Q equal to 0, so that there are no holding costs. And then the only cost per cycle would be K. So we'd pay only K per cycle, but we'd pay it an infinite amount of time, an infinite number of times in a fixed amount of time. So what we really want to do is minimize cost per time unit. For example, we might want to minimize cost per year. So that makes it a little bit more difficult. So how do we fix it up? So the length of the cycle is T. Let's say if lambda is measured in units per year, then T is in years. How many cycles are there per year? The answer is 1 over T. Just to make sure that's clear, if the demand rate is 1,200 units per year, Q is 100, and the length of a cycle will be 1 month, or 1 over 12 years. And there will be 12 cycles per year. So what is the total cost per year? The total cost per year is the cost per cycle times the number of cycles per year. So we take our cost per cycle, we multiply it by the number of cycles per year. We plug in Q over lambda for T, do some simple algebra, and now we end up with another equation. And this is the equation that we want to minimize to get the lowest cost. Okay, so as we mentioned, it's a trade-off between the fixed part of the order cost and inventory holding cost. So our inventory holding cost as a function of Q looks like this. Our order cost as a function of Q looks like this. We add them together. We're hoping to find the minimum of that total cost relationship. That will be the EOQ, or the economic order quantity. All right, so we take the derivative. That's easy. We take the second derivative to make sure we're getting a minimum, and we are. So we set the first derivative equal to 0, and we solve for Q, and we get this equation, right? So this is the equation for economic order quantity. If you look at it to see if it makes sense, if the fixed cost per order is bigger, if K is bigger, then Q is bigger. We order less frequently because of the high fixed cost. If the inventory holding cost is high, then Q is low because we want to carry less inventory. So it kind of makes sense. All right, so that's a simple model. You might have even learned it in Eco 1, I'm not sure. But it had some deficiencies as far as assumptions go. For one thing, demand is never known and constant. It is pretty much always random, uncertain. Other things we might consider: how often do we decide whether to place an order or not? So are we kind of making this decision continuously, or do we only make this decision every so often? What about lead time? There's always lead time for real problems. And whenever you have random demand and lead time, you will have back orders, or you certainly will risk back orders. So this is my attempt at drawing what a real inventory problem typically looks like. So we see that demand as it goes downhill is now a squiggly line, not a straight line. That's my attempt at showing that it's random. And we're going to have what's called a reorder point. And so what this means is that when inventory hits this level, we order more units, or we decide to make more units, right? But in the real world, we cannot make these new units instantaneously. It takes a certain amount of time for those units to arrive to our inventory. So that's called the lead time, the order lead time. So even though we reordered inventory at this point in time here, we did not receive it until this point in time here. And so in between, the inventory continues to go down. The order arrives and our inventory jumps back up. When it goes down, we hit the reorder point again. So we order more this time. It kept going down at a little bit faster rate because of randomness, and it actually dipped below 0 before our replenishment order arrived. And so here we have back orders as a result of that, right? This is kind of what the typical inventory problem looks like. And so you can consider problems like what should be the reorder point and what should be the order quantity, right? So basically, what is Q and when should we order Q? In the simple model, we could wait till it got to 0 because there was no lead time. Okay, so there are various kinds of inventory policies. When to review inventory levels. So typically now inventory is reviewed continuously. But back when I was your age, that was not the case. So you may have heard of maybe you watched an old TV show where people were taking inventory, which basically meant you go through the warehouse and count how much stuff is there. That's actually what they did. So people, companies would not know how many units they had in inventory unless they specifically went out and counted them. So you might count the units once a month. And once you find out how many units you have, you place an order for so many. Nowadays, this is all kept track of instantaneously on computers. And so you know all the time what your inventory is, and you can have this so-called continuous review policy. How much to order? There's a couple of versions of this. You can order up to a certain amount, or you can have a fixed quantity order size. But probably the most well-known is the RQ policy we showed in that graph. So when inventory hits the reorder point R, order Q units. I think that's something we're going to look at in one of the problems on the homework. Okay, the second model we're going to talk about is news vendor. I actually think this is more interesting. And we actually talked about this example last week. And so the setup is that in the morning, the news vendor has to buy newspapers from the newspaper company. The vendor stands on the street corner and sells them. And at the end of the day, any leftover papers are worth way less than they were. You might get some possible salvage value from the recycle center, but basically they're not much use at all. So there's no setup, no lead time, and it's a one period problem. Now, the important consideration here is that demand is random. So this is a fundamental model that considers the impact of the fact that demand is random. That's so this problem arises all the time in many different settings because it's a very fundamental model. Okay, so the decision variable is how many newspapers to buy at the beginning of the period. All right, so we're going to call that Q again. And then there's the demand. The demand, however, is a random variable. We do not know what it's going to be. We do assume we know what is the distribution of demand. For example, you might be able to have historical data on the demand for papers every day, and from that you could get the demand distribution. So we can compute some basic quantities here. So if Q minus D is positive, that means we ordered more papers than there was demand for, which means we have leftover papers. This expression, maximum of 0 and Q minus D, will be leftover inventory at the end of the day. And the opposite of that, if demand is larger than Q, then we sold out of papers and we lost out on demand. So this quantity here is our lost sales. All right, I'm going to stop sharing my screen just for a second. See how many people are ghosting me. Oh, come on, guys. Unghost. All right. Okay, that's not too bad. Sheena, you're in trouble. Sorry, Peter. All right. Back to the presentation. All right, so we have leftover inventory given by this expression, lost sales given by this expression, and then sales is whichever is smaller, the number of papers that demand. So if we bought 10 papers, we cannot sell more than 10 papers. If demand is only 5 papers, we can't sell more than there's demand for. So the minimum is a sale. So we have 3 cost parameters: how much we sell the papers to the customers for, how much it costs us to buy them from the newspaper company, and then the salvage value of leftover papers. Okay, why aren't you? There we go. So there's kind of 2 equivalent formulations. One thing we can do is maximize profit. So this first term here, this first term here is the number of papers we sell. And the profit we make on each paper we sell is P minus C. We sold it for P, cost us C to buy the papers, right? This is the number of leftover papers, and the profit we make on that is S minus C, the salvage value minus the cost to purchase them in the beginning. There's another way to look at the problem, and it's kind of from a cost perspective to minimize cost, right? So this is based on kind of an underage and an overage view, right? Underage means we didn't order enough papers, we didn't buy enough papers. So this is our underage is given by this equation here. And the cost is the lost sales, right? So this is a profit we would have made if we weren't under by this many papers, all right? And this is the overage cost, all right? If we have too many, the profit we make is C minus S. Wait, I mean, that, blah, 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 excuse me. The cost is C minus S times the amount of over newspapers. This is if we order too many. So these are equivalent formulations, by the way. This is the one that makes the most sense in the context of this problem. This is the one that people typically use, though. We talk about underage costs and overage costs. Okay. Now, if we look at this, we have the cost of underage and the cost of overage. So the term S minus C must be negative in the cost model. So the salvage value should be less than the cost of the newspaper, or equivalently, the cost should be more than the salvage value. Why is that important for this model? Somebody who's actually listening can open your mic and tell me.
If the salvage value was higher than the cost, then the model would just say to like buy infinite newspapers because it'd have a higher salvage value than the cost.
Perfect. That's exactly right. Oops, I'm trying to erase that, but I can't because yeah, I had that covered up. Yeah. If the salvage value was more than the cost, you'd buy an infinite number of newspapers because you couldn't lose money even if you were over. Okay. So the general setup is we have Q, that's our decision variable. D is our demand. When we did this last week, we had demand scenarios. But here we're going to know the distribution of the overage cost, CO, the underage cost, CU. And we have the cost equation, so this is what we want to minimize. Math here is all calculus based again, although it's much fancier. So what we want to do is minimize actually the expected value of this cost function, where expected value is taken with respect to the demand distribution, which we assume is known. All right, so this much I expect you to know. I know you know what an expected value is, and I know with respect to what with respect to what distribution. All right, so when we write out the expected value of the two terms, we can expected value is always an integral of the function times the demand distribution, integrated over the range of the random variable, in this case, demand. Now, I'm going to go fast here. I guarantee you could follow the math if you wanted to, but math to me is just not all that exciting. You can fool around with the limits of the integral because of the max function here, right? This is only positive when x is less than q, so you can get rid of the max and just have x go from 0 to q because it's 0 above q. And here we've got x minus q, so it's the opposite. Here you have to integrate from q to infinity, and you can get rid of the max functions in the two integrals. So now we have simple integrals to do. So this is our expected cost up here. Now we have to take the derivative of this equation with respect to q. So I don't know if you remember how to take derivatives of integrals. I know I didn't. I had to look it up. It's called Leibniz rule. This is Leibniz rule. It allows you to take the derivative, and you end up with this equation where f is the cumulative distribution function of the demand distribution. Check the second derivative. Okay, so we set the first derivative equal to 0 and solve for q, and what you end up with is this equation. Okay, so now we have to interpret this equation. So what we're looking for is the value of q that makes cumulative distribution function equal to this ratio. Stated differently, if this is the demand distribution, we want to find the value of q such that the area to the left of q is equal to cu over cu plus c0. Right? So we solved this news vendor problem last week in Excel using scenarios and minimizing average cost or maximizing average profit. But that was only an approximate method because we use scenarios. Here we can find the exact solution for any demand distribution, right? So that's kind of cool. All right, let's look at a couple simple examples. We're going to make one last production run. We have an overage cost, an underage cost. Demand is known to be normally distributed with this mean and this standard deviation. So we plug those numbers in. The CO over CO plus CU is 0.75. So we want to find the value of Q such that 75% of the demand distribution is to the left. So what value of Q gives us that? Well, you can look it up in your normal tables, or in Excel, you very easily just use the norm inverse function, right? So in Excel, you type in equals norm inverse, the probability, the mean, and the standard deviation, and it tells you what that value is, right? So that's how many we need to order. Now, granted, this should probably be an integer value. However, our demand distribution is continuous too, so we're just going to round off here in this case. Let's look at another example that's closer to the business game. Suppose it costs us $4 to produce. It costs us, we sell it for $7. The selling price, if we get back orders, is 80% of $7, plus there's a $3 inventory holding cost. Demand distribution follows this normal distribution. So our underage cost is entirely lost sales. So the price we sold for is $7, manufacturing cost is $4, so it's $3 per unit lost sales if we're under. And in the case of the overage cost us $4 to produce, and our salvage value is the 80% of $7 we get minus the $3 inventory holding. So basically, we just converted this into a news vendor problem. We have a CU and a CO. So we compute those values. We get the ratio, plug it in the norm inverse with the right mean and standard deviation. It says we should order 3,142 units, right? So we solved this problem last week using Monte Carlo simulation, or by using scenarios, the same thing. So why would we even want to do that? Well, it's because this news vendor problem is a very specific problem with a single overage and underage costs. But if we had more complicated problems, we might be able to still solve them with Monte Carlo. So I have a couple examples. Oops, what did I do? I screwed that up, but okay. What do we have here? I got to remember this example first. Okay, this is the one we just, the example we just did. We solved it simply by using norm inverse in Excel, and we got the answer of 3142. Just to show how you would do it in Monte Carlo, I generated observations on demand. I generated them.
Professor Sturr, we cannot see your screen.
Oh, thank you. All right, let me start over. So this is just solving the same problem we just solved on the PowerPoint slides using Monte Carlo. So in that problem, demand was normal with a mean of 3,000 and a standard deviation of 300. And the CO over CO plus CU was 0.682. And the answer turned out to be 3142. So what I did instead was I generated 100 observations on demand. So those are my 100 demand scenarios. And I generated them from a normal distribution. And this, by the way, is the Excel way you could generate from a normal. You have to put an equal sign in front of it. So you type equals norm inverse, and then rand, open close parenthesis, the mean and the standard deviation. So that's how you can generate these demand scenarios. And then basically you decide the number of units to produce here. You compute your total cost. And then at the very bottom, you compute the average cost. So this is just the average of column G. So we're trying to minimize average cost, and this is our decision variable. So we have a simple solver model. One decision variable, one objective, no constraints. Right, so this average cost is our objective. We're trying to minimize it. And by changing this value here, cell A2, and we solve it, and it solves very easily. And we get 3141. So we're off by 1 unit. So why is that? Well, it's because of sampling error, right? Because it's only an approximation. Oops. Our 100 demand scenarios only approximate our normal 3,300 distribution. All right, give me a second here. All right, the next example really is not much new. Sales price, production cost. Leftover units can be sold the next period. Back orders sold. Yeah, I mean, this is basically exactly the same problem. Just for grins. I think that's it. That's one of the examples posted. It's just a little bit more complicated, but the idea is pretty much exactly the same. You have random demand scenarios generated from a normal distribution. You have your decision variable. And the only thing here really is that the costs are more complicated. You have various, profit. You have revenues and costs that you have to compute. Ultimately, you get a profit over here and you maximize average profit. So there's really nothing new about this example. And the last example we have here, multi-period problem. Okay, so in the beginning, we start with 53 units of finished goods. We need to decide how many to produce in period 1 and how many to produce in period 2. We have back order costs, inventory carrying costs, loss of goodwill costs, revenue from regular sales, revenue from back order sales, and salvage revenues. This is a more complicated model. And this one might be worth looking at. Okay. So here it is. So we have two decisions. The amount of units, the Q, the amount of units for period 1, the amount of units for period 2. Okay. So our demand scenarios consist of the demand in period 1 and the demand in period 2. Right? This is the initial inventory we have coming into the problem. So, and this is how many we decide to buy. So if we buy this many units and the demand is this many units, we'll sell a certain number And we might have inventory we carry over to the next period, or we might have zero inventory and rather have back orders that have to be met the next period, right? And then, so then it kind of repeats. We have demand for the next period. We produce this many. Then we have back orders that we sell that were held over from period 1, regular orders for period 2. We may have leftover units at the very end, in which case there's salvage value, or we may have back orders left over at the end of both periods, in which case there's a cost associated with that as well. The interesting thing about this is that it is a 2-period problem. Right now, here's the catch on this problem. We have to decide the number to produce in period 1 and in period 2 at the very beginning. We decide those before anything else happens, right? So in that being the case, it's a fairly easy problem. We have 2 decision variables, production in period 1, production in period 2. And then we have our average profit as our objective function. Our solver model, again, is very simple. In this case, we have 2 decision variables. We want to maximize our profit, average profit, I should say, and it solves pretty easily. All right, so does anything seem unrealistic to you about this? Feel free to unmute yourself. Nobody? So is this how it would work in the real world? In the real world, would you have to decide how many to produce in period 2? Oops, sorry. Would you have to decide how many to produce in period 2 at the beginning before period 1? The answer is probably not. You could produce in period 1. You could observe demand, right? And then before the start of period 2, you could decide how much to produce in period 2. Now, the question is that a harder problem, or why is it harder? Anyone care to speculate? Hearing none, I'll say good, because that's also a homework problem. Let's take a quick look at the assignment. I think I got 5 problems. All right, so we just looked at an example 4. Problem 1 is it says that this can actually be solved analytically using our news vendor model. So it says solve it using the news vendor model analytically. So we have blah, blah, blah. Now, it's just like the news vendor problem, as random demand. But now what's different is that the salvage value is also a random variable. At the beginning of the day, you're not sure what the price, the salvage value you're going to get the recycle center is. So X, this is also a random variable. So we have 2 random variables in the model. So the question is, can you figure out how to solve this problem in Excel using our scenario-based Monte Carlo simulation? Okay. Not only are you going to solve that problem, you're going to solve it 5 separate times using a fresh set of 100 scenarios each time. And then based on those 5 solutions, you're going to form a 95% confidence interval on the number of papers to buy. And then you're going to answer this question about how to decide how many scenarios you should use in a model like this. Okay, problem 3, we have a multi-period news vendor problem, which is kind of like example 5. Problem 4 is, this is one of my more favorite problems. We have 20 days worth of demand data. So we have 100 scenarios for each of 20 days. You have to decide basically what to do each day. And I thought I had a fifth problem in there. Maybe I don't. Guess there's only 4.
There's a fifth one on course site.
Okay, I opened the wrong one. Let me open the one on course site. Gosh, I wonder if those are the same. Hopefully those are the same problem. All right. All right, so those were basically the same. The ones I showed were the same first 4 problems. The fifth problem is this. How does variance in demand affect profits? So we're going to consider a news vendor problem with a particular underage cost and overage cost. Then we're going to have the mean demand is going to be the same, right? I didn't actually give you a mean. That's interesting. I'll have to change this because I think I wanted it. I should say something like this. The mean is 500 units. So that's the mean demand. We're going to solve this news vendor problem using values of sigma equal to 15, 50, and 100. That should be really easy. And so the question is, will the variance affect your profit? And if so, how? And if so, why? That seemed to make sense. One of the things industrial engineers learn for sure is that you can't do everything simply by using means and averages, right? If all that mattered was the mean demand, it wouldn't affect the variance. The standard deviation would not affect profit, would it? Let's see if it does. All right. I'm done with today's lecture. Does anybody have any questions about anything? Let's see if we got any more ghosts. I better see.